Okay, now let's just put all this in a little bit of context. For an LC circuit, the differential equations L di dt plus Q over C equals source voltage, maximum source voltage times the cosine of omega t. And I put a theta naught in here for a phase angle. The reason is we want our current to have zero phase angle, and the current's not going to necessarily be in phase with the driving voltage. Okay, so we solve the equation. First of all, we rearrange it. Divide both sides by L. Then replace current with dq dt. So we have second derivative q with respect to t here. So we have a second order equation. We get our characteristic equation. We get our characteristic solution, which is a cosine omega naught t plus some theta hat. Theta hat is arbitrary, and A is arbitrary, allowing us to satisfy initial conditions about whenever, for example, we start the circuit, maybe what the voltage on the capacitor is, or the charge on the capacitor at the initial instant. And we get this. Omega naught is 1 over the square root of LC, as you get directly from the characteristic equation. The solution to the particular equation would be a linear combination of a multiple of the cosine of omega t plus theta naught and sine of the same argument. And plugging that in here, plugging it out throughout the problem, we're going to get some value of b and some value of theta hat, such that our particular solution is b cosine of omega t plus theta hat. Now this is if we don't have the condition where omega equals omega naught. If omega equals omega naught, then we have a resonance, and we'll talk about that in a minute. Okay, so right there is our solution to the fairly simple case here. And most of the cases we have, we're not dealing with the particular solution because we're not going to drive this this circuit with a specified voltage. Instead, we're going to assume, as we've already seen, a current function. I equals I max cosine of omega t, and then we're going to figure out all the rest of the quantities in terms of that current function. So we don't really need the differential equation to solve that particular case, but we want to put it in the context of the differential equations, which are really what justify the solution. Then in LRC circuit, we have the same terms we have in the LC circuit, but we have the voltage drop across the resistor, which is R times the current being dq dt. Gives us this solution, this equation. We get a characteristic equation, e to the mt being our tentative solution, our assumption. I'm not getting the right word, but we're going to get characteristic equation m squared plus r over ln plus q over lc equals 0. Solution to that's very straightforward. From the quadratic formula, we'd end up with negative r over 2l, and I'm going to read it to you. This is what we end up with. And that's oscillatory if this thing is under the square root sign is negative, and you should be very familiar with that. And that occurs if r is less than 2l over c, as you can verify by setting this quantity less than 0 and solving the inequality. In that case, then, we have an omega naught natural frequency of the system that's equal to that natural angular frequency equal to this quantity. And I factor out an r over 2l here to get this form. And that kind of fits in with what we have up here, the r over 2l. First of all, the r over 2l is going to give you the characteristic solution, a e to the negative r over 2lt times the cosine of omega naught t plus some theta hat that depends on the relative sizes of L, R, and C. Then you have a particular solution of the form b cosine omega t plus theta tilde, which is what we have over here, where b and theta tilde are not arbitrary. They come from the particular solution, and they depend completely on the values of L, C, and Vs and I suppose of theta hat here, theta naught. We get this solution, okay? Now, you're not going to be asked to do this, just giving you the context, okay? If omega equals omega naught, then we get a large value of B, and that gives us resonance. And actually, I think that's kind of a stupid statement there, so I might want to remove it. Let me think that through. Okay, it's not the smartest statement. We want to leave it there. You can work the details of that through. Okay, so in the case where you have resistance equal to 0 and omega equal to omega naught, you have a particular kind of resonance. So you have no resistance, so that you don't have any dissipation of energy. So what you end up with, you also end up with a repeated solution. That's the only way omega can equal omega naught. And with R equal to 0, so forth. So you get a particular solution of this form. Remember, if you have a repeated root, you're going to have a B cosine of your argument plus a CT times the cosine of your argument. And the CT is going to increase without bound. So you have resonance with eventually increasing amplitude. And what I mean by that is the amplitude can do some funny things at the beginning, so I'm just going to put a little squiggle in here to say that there's things that happen in the early part of the development of the resonance that depend on the B cosine omega naught plus theta hat and the sine of B. And I'm not going to go into the details of that, but eventually this, which maintains constant maximum magnitude of 1, is going to be obliterated by this, which has a magnitude that increases without bound as t increases. So we get this sort of thing. The frequency stays the same, but eventually the amplitude, and actually usually fairly quickly, the amplitude will start growing without bound according to pretty much a linear progression. I'll mention also the nature of this solution. This is going to exponentially decay. So you have an oscillation that exponentially approaches 0, but your particular solution maintains a constant amplitude, so that after this decays, this takes over. So that the characteristic solution is transient. Transient because it only occurs for a while until t gets big enough to make this practically 0. But then this is, we'll say, sustained, so that as t becomes large, this is what's going to happen. And the value of B is going to depend on how well omega matches omega naught. If omega matches omega naught well, you're going to have a large B, so you're going to have a pretty big amplitude. And that's what we mean by resonance, and that kind of further explains the relatively stupid statement I made before.